start introducing our speaker. So our speaker today is Benjamin Wallisch. He's going to tell us about some power spectrum probes of the early universe. Ben did his PhD at Cambridge and then did a joint postdoc with at UCSD and Princeton, and is now doing another joint postdoc between Stockholm and University of Texas at Austin. So very happy to have Ben here today and looking forward to the talk.
Yes, thank you very much. It's great to be here, talk to all of you, especially also kind of working. I've been working with Cynthia and Srini kind of remotely for a while now, so it's great that we can finally do that also in person. And yeah, as you heard, I seem to have a thing for like being in two places at the same time. In fact, even during my PhD, I spent time both in Cambridge and in Amsterdam. So that's where all of that started already. And yeah, today I'm very happy to tell you about some work I'm doing together with Katie Fries in particular, Gabriele Montefalcano on the one hand, and then some other work together with Dan Green, Yi Guo, and Jashu Han that are both related to kind of the early universe and using the power spectrum to probe it. And so in general, if you have any questions, please feel free to kind of interrupt at any time. If I'm not getting kind of all the way through my talk, that's completely fine. I can just kind of summarize it in the end. And so, yeah, let's all have fun together here instead of me just giving kind of a 50-minute kind of monologue. And so to get started, I want to start with kind of this kind of house of cosmology as I'm thinking about it. Just very broad. I think like general relativity is a very kind of broad kind of basis and foundation for all of the work that we're doing in cosmology. And then I think of it as it being resting essentially on three pillars. One of the pillars is just the initial conditions, whether they're coming from inflation or some other mechanism, that's essentially to be seen. But that's kind of one kind of pillar that we're both kind of resting on, as well as also testing using our observations. Secondly, we build on the standard model of particle physics. It's like all like what we often call like baryonic physics that's going on, and all of that, and especially in the early universe, of course, all these processes play a huge role. So that's the second pillar. And then, of course, this third pillar is like all the stuff we don't know. Or like in terms of the energy density today, of course, like 95% of the energy density today is made up of like the dark stuff, so in particular dark matter, kind of dark energy, potentially also dark radiation. And so essentially all the energy densities that we can describe, just put it dark in front because we have no clue what they are. And we know that there is dark matter and dark energy. We only have limits on dark radiation. But I'll be talking a bit about that later.
How can something we don't know be a pillar?
Well, I mean, in particular, otherwise, how do we grow structures? I mean, essentially, this kind of, can think of it, okay, we start out with the initial conditions. We have fluctuations in the early universe. They grow under the influence of gravity. Kind of with like, we have like the baryons there, but in order to really kind of get the structure formation that we see in our observations today, we do need the dark matter. Otherwise the universe will look completely different. And of course, in the late universe, we also need dark energy to get that accelerating expansion. So in that sense, it's a pillar. But at the same time, I guess it's not that they're kind of very uniform pillars and we understand them very well. All of these parts do have cracks and things that we definitely still have to understand and patch up, etc. And so it's both both pillars as well as very much each of them active areas of research in order to try and kind of better understand them, in order to kind of actually kind of make this house at some point stable, hopefully. And so this is kind of one kind of very kind of high-level theoretical view of cosmology. And then, of course, on the other hand, we've got a whole host of observations today. I think it's really exciting, all the probes of the universe that we have today. We have, in particular, if you go kind of chronologically through the universe, you've got the kind of the hot Big Bang, which is like furthest away. Kind of going further in, at redshift about 1,000, we of course have the release of the CMB. Today, this serves in particular as two very important probes. On the one hand, of course, the anisotropies. On the other hand, the spectral distortions of the black body spectrum that serve as kind of very unique probes of a lot of different kinds of physics. And then, of course, at kind of later times, when we then have more and more structures forming, we can use kind of line intensity mapping, which is more of a future probe at this point, but I think will kind of really kind of take over the field in the next like 10 to 15 years, as well as, of course, galaxy clustering, such like measuring the positions of galaxies in the universe to trace the large structure density field. And then kind of mostly kind of more closer to home, we, of course, now have like direct observations of gravitational waves. Also, with kind of PTAs and nanograph, we now have really kind of good indications for the stochastic gravitational wave background. And then, of course, we could also dream about just the primordial gravitational background and kind of detecting that at some point. So it's kind of really vast. And so we somehow have to kind of analyze kind of all this data that we have. And so there's a lot of different ways that we can kind of treat our data, that we can statistically kind of analyze it. Of course, the most popular and the most well-developed way of doing it is using a two-point correlation function or power spectrum. The universe is kind of very Gaussian over kind of a long kind of part of history. And so kind of the power spectrum, of course, is kind of very well tasked to kind of to describe that. But then, of course, we know in particular, if we look into the late universe is inherently kind of non-Gaussian, given that gravity is a nonlinear force. And so we have all these other kind of statistics, whether it's kind of higher point spectra or kind of various other ways of kind of building summary statistics, skew spectra, Kurtz spectra, just looking at one-point statistics. It's kind of various kind of ways of just like trying to find summary statistics. Or then, like particularly in recent years, more and more people are thinking about actually kind of analyzing kind of the maps directly, whether it's the CMB or kind of essentially the galaxy maps, or it could be cleansing maps. Then we really kind of, in principle, that's then all the information that is in the data that we can then kind of extracting or that we then analyzing. Related to that, not doing kind of the analyses based on kind of spectra, so kind of higher point functions, but actually at the field level. And so really kind of analyzing the perturbations essentially themselves, or then kind of using more machine learning type approaches with like implicit likelihood inference, which also referred to as like simulation-based inference, for instance. And so that's a whole list. I mean, we could go on and on and on, given that what we want to analyze is kind of a non-Gaussian field. But what I'll be doing is I'll just be sticking to the first one here, which in some sense is the easiest. Secondly, it's the most well understood and theoretically kind of best described. And as I will show you, it still contains more information that we haven't extracted so far that we can still do. And so we can really use that our kind of the knowledge that we can build up about this observable or these observables based on a two-point function in the past to extract more information and then kind of make our way kind of step by step to kind of these more complicated statistics. Okay, so the plan of my talk is first I'm going to be talking about the CMB and larger structure as the two main probes that I've been kind of using in my research. And then as kind of two examples to kind of probe the early universe, I'll be talking about free streaming neutrinos as well as primordial non-Gaussianity. I had mentioned in the abstract I might also be talking about primordial features. If you're interested in those, then we can do that at the end of the talk. All right, talking about the CMB. Well, so that's the CMB. It's a background light photon with a black body spectrum with a temperature of 2.7 Kelvin. That's the workhorse of cosmology. Well, OK, it's not quite that. It's, of course, the anisotropies that we're looking at. These fluctuations at the level of 1 in 10 to the 4 that we see around this kind of mean temperature of 2.7 Kelvin. And so if you kind of analyze it, if you compute the two-point function or the power spectrum, so if you kind of correlate kind of any 2 points on the sky with a given kind of angular separation, what we get is this two-point function. And so in particular, the two main features are kind of these oscillations, which are the baryon acoustic oscillations, and this overall kind of damping tail. With one kind of apology to all the SPT people in the room, this plot is a kind of few years old, so I should update it at some point. So this tail here is kind of very much kind of filled in with data now as well. And so what we see here, as I was saying, is the baryon acoustic oscillations. And what are they? They're actually just sound waves in the early universe. At very early times, so before redshift of 1,000 or about like before like about 400,000 years after the Big Bang, photons and baryons are very strongly coupled together. And so we also know from the initial conditions, we have perturbations in this photon baryon fluid. They excited sound waves that we can kind of relatively easily describe with just this kind of harmonic oscillator equation, where we have like pressure is kind of forcing outwards, and we have gravity kind of as a driving force and connecting all the different sectors at early times, leading to sound waves. In particular, we have the photons and baryons, they directly interact, but otherwise talking to neutrinos and dark matter only through gravity. And so if you solve this equation, we get a simple oscillator equation, of course. With one, okay, we have these oscillations with other sound waves with a certain kind of sound speed, which is just given by c over c squared over the square root of 3, just slightly modulated by the presence of baryons, as well as kind of the initial conditions that are encoded here in this kind of A. Now, importantly, I didn't write down the sign solution here because the coefficient of the sign is actually kind of 0 if we're assuming adiabatic initial conditions. So we're starting out with just a pure cosine in the present if you assume adiabatic initial conditions, which we only have evidence for in the universe. We only have upper limits on kind of non-adiabatic initial conditions. And so these sound waves is what we then see not only in the temperature or intensity power spectrum, but also in polarization and the cross term. And so this is the famous kind of Planck temperature anisotrory map, and this is the Planck polarization map on the sky. Great. So that's as much for now that I want to talk about the CMB. So let's continue with luster structure. First of all, on the one hand, we might say, well, I mean, we've been gaining so much information from the CMB. It has so much information. We haven't even extracted all of it. So why should we consider luster structure kind of in addition? Well, I think at 0th order, it's just kind of additional complementary information that we can gain about the universe, including, of course, especially kind of towards later times, as kind of snapshot at later times, but at the same time also, it encodes like all the evolution, the evolution of the perturbations from earlier times as well. Now, in addition, if you look at it from a more statistical perspective, at least in principle, there's many more modes available in luster structure than in the CMB. Because in the CMB, we just have this we always have this just the 2D sky kind of around us with the CMB, whereas in large structure we can really probe the 3D density field of the universe. And so just like if you go to smaller and smaller scales, roughly, I mean, for the CMB, things scale as kind of multiple squared, whereas kind of roughly speaking for larger structures scales as like wave numbers cubed. And so going to smaller and smaller scales, of course, cubically is kind of much faster than with the square. And so that is related to why, in principle, there's much more statistical power, and we can, in principle, also access much, much smaller scales. I've already said kind of in principle here. I'm coming back to that kind of in a second. And then, kind of lastly, there's a huge observational effort going on in kind of large structure at the moment. So I think there's like BOSS and DESI, BOSS and kind of DES. Things have been kind of something kind of slowly kind of been gearing up. But now, I mean, like DESI had first light. They will have the first kind of big data release kind of next year. Rubin is coming online in the next couple of years. Euclid is flying. Spherex is currently being tested at JPL, and is going to fly soon as well. I mean, Roman is gearing up. So there's a huge, we're just going to be flooded with large structure data. And so this is really kind of another window in the universe, and so I think we should really kind of take advantage of that as well, even though it comes with its own challenges. Question.
Can you clarify what you mean by access to smaller scales in principle?
Yeah, so I come to the in principle part in a second. But so I mean, if you look out in the universe, we can map the universe, including like even down to like galactic scales. We can just look into telescopes, take pictures, and do whatever, take spectra. Now the question that in principle, of course, comes in: how can we use that? Can we utilize that information, or what does it require for us to utilize that information reliably? I'll come to that in a second again. And so there's also quite a large kind of range of different large structural observables, especially kind of galaxy clustering that has been kind of similar to kind of the CMB temperature and really being kind of the workhorse of galaxy structure analyses, but also kind of especially with DES and then in the future kind of Rubin, kind of LSST, kind of weak lensing is trying to kind of really kind of make a push, and it does have kind of quite a few advantages in terms of like photometric redshifts as well. And then kind of at higher redshifts, we have the Lyman alpha forest. We of course have galaxy clusters. In principle, I could have also kind of put on here kind of CMB lensing, KSZ, TSZ as kind of the CMB secondaries, which in principle are also kind of larger structure probes. So we have all of these kind of, what I'll be kind of focusing on is going to be kind of galaxy clustering, which I think we have kind of a lot of kind of also like analytic control and understanding. So it's relatively, by now, kind of relatively robust probe of the density field of the universe. And so if you kind of look at this kind of map of galaxies, every point on here is a galaxy. And again, if you do something similar as in the CMB, if you take the 2-point correlation function and Fourier transform it, then we get this characteristic kind of metapower spectrum that's shown here with overlaid kind of data points from essentially the inferred metapower spectrum from Planck or from DS cosmic shear as well as from kind of the SDSS surveys, kind of even with the Lyman alpha forest and kind of going to kind of relatively small scales. Now, here you can see this kind of ominous dotted line here. That's a very important dotted line, actually. What I'm showing here in solid, that's the linear metapower spectrum. And so, but what we're actually measuring, if we kind of look out there, is the dotted line here. That's the nonlinear metapower spectrum. So gravity is inherently nonlinear, and hence we have we have like additional growth of structure just through gravitational nonlinearities on small scales. And so essentially, this is kind of the name of the game for a lot of larger structure analyses, the goal is to kind of go to smaller and smaller scales, which however means that we have to better and better understand and be able to compute the effect of gravitational nonlinearities. Joachim?
Why aren't the data points match the dot?
Well, they are, so they measured kind of essentially here. Now, okay, that's two points. One is, especially alignment of a forest, those are observations at higher redshifts, like beyond 2. So it's more linear. And so this dotted line here, that's the nonlinear metapower spectrum at redshift of 0. So that's kind of one. And two, like all these measurements have been essentially projected, essentially like through like a process such as like reconstruction. So we measure the nonlinear spectrum, and then we just kind of with kind of either like perturbation theory or kind of simulations or whatever, we then infer or we try to infer what the underlying linear metapower spectrum would be, and so that's what the plots the points are that are shown.
But like the LRGs go out to 0.5, right? The SDSS LRGs.
Yes.
Yeah.
Yeah. I mean, so they like on this plot. I mean, so of course, like DR7 now we are like post DR12 had two redshift bins, one from like 0.2 to 0.5, the other one from 0.5 to 0.8.
Yeah.
But you see like those points are stopping here around like K of like 0.2, 0.3. And so that's the range. Like that's also like that's really kind of the boss range. That's also the data that I'll be showing later. And then yeah, like the weak lensing, they are really kind of living kind of in this kind of higher wave number regime, which comes with its own issues and stuff like that, which I won't be kind of talking about, given that also I'm not touching kind of weak lensing data for now. Okay, and so yes, as I was saying, like okay, there's one is gravitational nonlinearities. Secondly, what we're observing, of course, in a galaxy survey in particular, are galaxies. We're not observing the underlying matter density field that I'm showing here. So we have to kind of relate galaxies to the matter densities. And so that goes by the name of biasing. And so that's another effect, in particular on these smaller scales, that is important and is capturing a lot of like astrophysics and baryonic physics that we, to be frank, don't really understand yet either. And so that's also kind of living here on these smaller scales, and it's something that we, in addition, have to contend with as well if we're analyzing galaxy clustering data. But on the other hand, we can also kind of play some tricks. And for instance, we can say, okay, let's not look at the entire metapower spectrum. That's hard. We can either call it, let's stop at kind of relatively small kind of wave numbers, like 0.1, 0.2 H inverse megaparsec. But then we kind of leave a lot of kind of statistics on the table. On the other hand, what we can also do is say, okay, let's decompose the metapower spectrum into like a smooth part, just like the overall broadband shape, and these oscillations on top. Now, these oscillations on top here, they are, of course, the baryon acoustic oscillations. And a lot of like both like the nonlinear physics, all the nonlinear physics, or most of the nonlinear physics, either from gravity or baryonic physics, is contained here in this broadband part. And so if you look at just the oscillatory part here, the baryonic oscillations, things are kind of much cleaner, and we have much better also analytic control over the observable, and we can go also to much smaller scales in analyzing the data. We don't have to stop at just like the nonlinear scale or kind of mildly nonlinear scales. And so what's great about this kind of what I'm calling the BO spectrum is it does capture the cosmic sound wave similar to, it's literally the same oscillations as we see in the CMB, and hence it's the same, it contains the same information about the early universe, the primordial universe. And what's great is that by now we really have the effects from gravitational nonlinearities on this observable under kind of very good theoretical control. And so we can go to relatively high wave numbers, essentially until the baryon oscillations are kind of inherently damped. So that's kind of one way of kind of getting more information out of the data by just looking at the part that contains the information that we want, but we have under better theoretical control. Great. Any questions so far? Say again?
How do you a priori split the data?
I mean, so in principle, what you can do, I mean, we can have we have a model for the overall broadband, but then if you want, you can one way that we did it, for instance, is you just add additional polynomial terms and can marginalize over them, and that gives and hence we get like the overall kind of broadband shape that we can then subtract. Any other questions? Yeah.
And were you saying we can only do this up to about 0.3 where we understand the broadband spectrum well, or are you talking about pushing it even further beyond?
No, I mean, so that split here,
yeah,
we can do to kind of relatively high kind of wave numbers. Now, I mean, the baryon oscillations are inherently damped,
yeah,
and so they kind of essentially gone by like 0.5, 0.6. So in that sense, it doesn't bias anymore kind of to go beyond that. But just kind of the split is we don't have to know anything about like the complicated like underlying kind of nonlinear physics to do that split. And these oscillations are damped also by gravity or by just like gravitational interactions. And so we do have to take that into account, but we can do that actually analytically. Okay, any other questions? Okay, then let's talk about free stream neutrinos. So neutrinos are essentially the second most abundant particle in the universe. They make up about 40% of the radiation density in the early universe, which means that they make up about 40% of the radiation density of the universe. And so, or in the early universe, they make up 40% of the total radiation, of the total energy density, which means that with the rest, the other 60% essentially being photons. And so, which means that they leave a sizable gravitational imprint in our observables, which means that we can detect their energy density. And the way that we usually parameterize this radiation density is in terms of this parameter n effective, where here we just split the radiation density in kind of the photon density and the neutrino density, which is here, and then kind of normalized such that it would be 3 if for the 3 neutrino species that we have, if the coupling of neutrinos at about kind of 1 second after the Big Bang was instantaneous, and if there weren't such effects or such things as quantum electrodynamics and kind of a few other kind of subdominant kind of loop corrections. And so including kind of those effects, in particular kind of non-instantaneous decoupling of neutrinos, as well as kind of QED, then pushes this number up from 3 to 3.044 is the latest number, where the theoretical error bar on this is actually like in the next digit that I'm not even showing. So these calculations now have been kind of very precise. I don't think we have to kind of really worry about kind of this number changing kind of dramatically in the future, in particular not in comparison to our observational abilities to constrain this parameter. And so what I'm showing kind of down here is the effect of kind of more or less radiation on the CMB temperature power spectrum when fixing the scale of, or the location of the first peak by fixing the angular size of the sound horizon, which is very well measured in the CMB. And what we see, the main effect here on the damping tail is kind of a decrease of power when we increase the radiation density. Yep.
This is naive, but how do we actually, what are the measurement constraints on 41%? Is it just subtraction where we know photon density and we know total radiation, so we subtract?
Well, it's essentially, essentially it's this split where the 40 instead of like the reason why it's 40, why it's kind of photons versus neutrinos being like 60-40, is just that photons are bosons, neutrinos are fermions, and so we have this Fermi-Dirac factor, as well as kind of the photons get heated, effectively heated when electrons and positrons annihilate after neutrino decoupling. Before neutrino decoupling, the only difference between the relative energy densities is just kind of the factor of like 7/8 between bosons and fermions.
Theoretical argument. What's the actual observational constraint?
The observational constraint is on n effective.
I mean, the abundance of elements.
Or yes, BBN. Yeah, that's right. Yeah. And so, yeah, the current constraints that we have from BBN are at the level of about like 8%. From kind of Planck, the constraints are at the level of like 5%-ish or whatever. Question?
Yes, so you said the error on the number is in the next digit.
Yes.
Although didn't that number become like from 0.046 to 0.44 recently?
Yeah. Okay. Like the number over the last like 5, 6, came down like 3.046, 45, 44. Now it might be even like 43 or something like that. Now, I mean, no, but so like the latest numbers like these 0.44 or 43. Now, so over the same time frame that the error on that has gone down. Like when we were quoting 3.046, I think the error that the estimate, the theoretical error that estimated was in the third digit. And so I think that the recent change, maybe from like 4.4 to potentially 4.3, that's mostly just a rounding thing. And so I think that especially like when you talk about CMBS4 or whatever, I think we don't have to worry at all, like whether that's now the 6, 4, 3, or whatever else. So yeah. Anything else? Okay. So as I was already saying, neutrinos are decoupling about 1 second after the hot Big Bang, so at a temperature of about 1 mega electron volts. And so they kind of since then they've been kind of free streaming through the universe, which in particular means that they are effectively traveling at the speed of light, whereas the information in the photon baryon fluid in the early universe, of course, only propagates at the speed of sound, so roughly c over square root of 3, which is smaller, which is kind of indicated here with these kind of perturbation profiles for kind of dark matter, photons and baryons, and neutrinos. So imagine kind of you just let go of a kind of an overdensity at the origin. Now it's a mass profile here, so it's kind of multiplied by r squared, which is why kind of this kind of shuts off kind of towards what's 0. So it's like r squared kind of times density. And so just letting it go, like the dark matter doesn't do anything. It just sits there. The photons and baryons kind of are traveling out. That's the cosmic sound waves, just the pressure waves due to the photon pressure. And then kind of neutrinos are also traveling outwards kind of similarly. And in particular, we see that they're traveling ahead of the sound horizon, given that they are faster, which also means that given their sizable gravitational imprint, they do drag on the photons and baryons and slightly kind of alter their the structure of these perturbations towards larger scales. And so if you look at this in the CMB power spectrum or in Fourier space, this is what we see. So what we see is that if we increase the amount of free stream radiation in the universe, the peaks are shifting to smaller scales, to larger scales, so smaller multiples in a very characteristic way. And so if you kind of look at that in detail, what we find is that we started out with this kind of perfect cosine in the initial conditions, and now the presence of these free stream neutrinos is inducing a phase to these oscillations. And so what's exciting is that free stream neutrinos are one of the few ways that we can produce this kind of coherent kind of phase shift that we see here, where with the other one essentially being the presence of isocurvature fluctuations in the universe. And so kind of measuring this effect of the phase shift in data is really kind of a direct way of probing the free stream nature of neutrinos, or more generally kind of dark radiation. And so this was the first time this was directly detected was in 2015 in Planck 2013 temperature data. And so the way that this was done is that we can essentially look at the spectrum. We extract the size of the phase shift, and then kind of look for that effect in data. And so together with Gab, I'm kind of going back to this analysis, and this is kind of the recent plot that we produced, which shows the template or the size of the phase shift as a function of multiples, where all these points here are kind of at the locations of the peaks and troughs in the temperature, polarization, and cross power spectra, with like showing kind of how much they are shifted away by the presence of kind of free stream neutrinos compared to if they were non-free streaming. Question?
Is the black your measured phase shift, or is that your template?
So, and it's okay. These are the kind of the data points that we get. So we measure those by averaging over 100 cosmologies, and then kind of we fit this kind of phenomenological model, which is motivated just by the two asymptotic analytic limits. One for kind of high multiples, we expect just a constant, given that in the deep radiation domination, it's really kind of the neutrinos kind of do their thing. Whereas kind of here, we then kind of transition into these modes, then kind of enter the horizon during meta-domination, and hence neutrinos become a very subdominant contribution to the energy density of the universe, and hence the effect here kind of shuts off towards zero. We can show that it's roughly in a kind of quadratic fashion in kind of to leading order. And so we have this kind of this template here that we then fit to these kind of data points, and that's shown here in the black curve with the band giving like the 1 and 2 sigma range for this fit.
Sorry, so I had a question. It's a bit naive. Would you mind going like 2 slides back? I was confused about here. So there's a shifting on the CMB, but the CMB is measuring the photons, right? So if I understand correctly, because of the neutrinos that are emitted earlier and they're free streaming, then they interact with the photons and they, in a way, like provide extra energy. There's like a boost of energy to the photons from the neutrinos that then make the shift in the CMB. Is that what's happening?
No,
or?
So it's purely gravitational. So that is, of course, given that there's so many.
The neutrinos change the gravitational field, and then that changes how they seem. Okay.
That's right. So I mean, if we go back to essentially here, I mean, essentially like neutrinos, after decoupling neutrinos and photons are only talking to each other through gravity. So this is kind of showing like the gravitational potential. And so it's only essentially like the right-hand side of the oscillator equation. And so that is then, if in the presence of free stream neutrinos, that changes, and hence then acquires a phase.
So it could be also even said that this is like neutrino lensing of the CMB, in a way, or pre-lensing.
No. Yeah.
Well, it is distorting it.
But it's
yeah,
physically pulling stuff around.
Yeah, well,
Yes. So
okay,
it is actually physically pulling stuff, right? It's not just that we look through something that gets distorted.
Right. So it's not a screen; it's actually fundamentals at the base.
Yeah. Okay. And so, right. Okay. And so having this template, we can then kind of analyze the data and kind of estimate, okay, how free streaming are neutrinos that we see in the CMB. And that's kind of the preliminary results they're showing here on the left. But first of all, based on Planck 2013 temperature data, what kind of Follen et al., which includes Marius Milea and Lloyd Knox, what they found was like a constraint of 2.3 minus 0.4 plus 1.1, which is like a more than 5 sigma detection of the free streaming nature, like of the presence of a phase, and hence of free streaming neutrinos. And so adding kind of polarization data, which is also shown here on the left, we kind of shrink this contour, given that in particular in polarization, the peaks are sharper. Then hence we can better measure kind of the peak locations, hence the phase shift. And so we do get quite a smaller error bar. Particularly this is relatively non-Gaussian, and so we quite Gaussianized now. And so far we've just done forecasts for kind of actin SPT. We're kind of actively running the analysis kind of as we speak, and we do expect kind of these error bars to come down by something like 60-70%. And then, especially with kind of SO and kind of S4, this will kind of go down kind of even more. And really, we should get like a few percent measurement on the free streaming nature with S4. Yoni?
So what kind of models would give you a different value for the n delta phi compared to n effective?
Right. So essentially, given that we now do n delta phi and n effective, essentially what we're doing, we can really kind of factoring out the phase shift part. And so that's really the free streaming part. And so what n effective covers like all the radiation, like the radiation density as a whole, including stuff that is not free streaming. And so imagine you have neutrinos interacting with themselves or with something else, whether it's dark matter or baryons or whatever, that kind of, whatever kind of decreases their free streaming length will kind of decrease the phase shift. In particular, the phase shift will be 0 if the free streaming length becomes shorter than the Hubble scale. And so essentially, a lot of things that you do in a neutrino sector, if you decrease the free streaming length, then you would have a decrease in the phase.
Okay, but like for example, like some like early axion or whatever would get you an effective, but not n delta phi.
Well, it depends. I mean, if it is kind of free streaming, if you have just an axion floating around, it's decoupled at very early times, then it will similarly be free streaming, unless it kind of clumps, it is kind of massive enough and clumps in the late universe or something like that. If you have like a milli-electron volt or like a micro-electron volt axion that's floating around, it decoupled at very early times, it will contribute to an effective according to kind of when it decoupled, and it will be kind of free. It will just be free streaming. It will be essentially propagating at the speed of light, similar to neutrinos, and unless again we do something that decouples to something else, or it behaves more like a fluid than free streaming radiation.
Analysis on the bin data, or do you do it on unbin data? Because in your plot you're showing that it's bin some.
And so we just use the Planck likelihoods. So yeah. Okay, and so something else that we're kind of working on at the moment, which I'm pretty excited about. At the moment, we're kind of just looking at the spectrum here, and kind of extract the phase shift kind of based on the spectrum. Now, at spectrum level, of course, we do have like gravitational lensing. In particular, we have effects like the ISW, kind of projection effects that are in there. Now, what we're doing at the moment is we're not kind of doing it on the basis of the spectra. We're now kind of extracting the effect at the basis of the perturbation themselves, and want to put them back into like the Boltzmann code to then really extract it at kind of the pristine kind of phase shift effect. from like a perturbation-based kind of template instead of like a spectrum-based one. And so then I think that's kind of the cleanest measurement we can get of the phase shift and hence of the free-streaming nature of radiation. Okay, we're doing on time. Okay, and so if we kind of go back to kind of this movie of perturbations, if we of course go beyond recombination, if we kind of let this kind of movie run forward, photons decouple, they do their thing, and then of course the baryons and the dark matter then form kind of the baryon acoustic peak here until at late times. That we can then kind of detect in our galaxy surveys as the BO as that I was showing earlier. And so from that it's clear that this kind of the phase shift should not only be seen in the CMB, but also in large structure. And so in other words, it should really be also seen in kind of the BO spectrum that I was defining earlier. And so that's what we did. That's exactly what is happening just on the theoretical front. What we also see is here for the BO spectrum, the peaks shift to coherently to larger scales. Now what's very exciting about the phase shift in particular is that I was talking about all these things about gravitational linearities, and it's like a mess, and we have to do a lot of work to actually get that information. Now I can actually show that the constant phase is very unique in the sense that it's immune from the effects of nonlinear gravitational evolution, meaning that it's unaltered from early times to late times, and we can just use linear predictions for the phase and search for it in nonlinear data. And so that's what we did a few years ago by kind of just adapting the standard BO analysis, which is essentially just kind of this part here, where the sound horizon is just varied by this parameter alpha. And so we kind of included an additional parameter, which we called beta, as just an amplitude for the phase shift with this kind of same kind of characteristic template that I was also already showing you in the CMB. And so we can do the measurement. That's what we see. The constraint is kind of very broad, just because we try to measure both a phase and a frequency at the same time with just essentially three oscillations. But we can get that a bit a bit tighter by including a prior on the BO frequency just from theta s of the CMB. And can actually get like a non-zero measurement at more than 99% confidence, even though, of course, the posterior peaks at very large values but we knew kind of going into the analysis that this would just be a proof of principle rather than like a very competitive measurement. Having said that, though, especially with DESI and Euclid, as well as kind of more futuristic surveys, this will kind of really greatly improve because we're going to have many more redshifts and many more kind of oscillations of the BO spectrum that we're going to be measuring to exquisite accuracy. Okay, any questions regarding that? Okay, in the remaining time, I just want to briefly talk about primordial non-Gaussianity as another probe of the early universe that we can use power spectra for. Now, this is just a cartoon showing that whatever kind of 2-point or higher point functions we measure in the late universe, whether it's kind of in larger structure or the CMB, we can of course trace them back to the initial conditions and potentially inflations or whatever other mechanism created those correlations. And let me kind of skip over that and just say let's look at kind of primordial non-Gaussianity. If you're kind of wondering more about this plot, let's talk about it later. And so one of the effects of primordial non-Gaussianity in large structure is this well-known effect of the scale-dependent bias. And so this is kind of an enhancement of the galaxy power spectrum on the larger scales coming from so-called local primordial non-Gaussianity, which is non-Gaussianity that is kind of with the largest amplitude in the so-called squeezed limit. So if you have like a bispectrum, we have like two kind of long wavelength and one short wavelength mode. And so what one can show is that kind of this from local primordial non-Gaussianity, this enhancement here has a characteristic 1/k² scaling. Now, where is this coming from? I was just saying that the local primordial non-Gaussianity correlates kind of two long wavelength mode with a short wavelength mode. And so essentially, where this enhancement of power is coming from is the modulation of short wavelength perturbations in the initial conditions by kind of a long wavelength mode of the gravitational potential. And so it's just as a toy model, if you look at kind of local quadratic non-Gaussianity, which is just kind of given by kind of the Gaussian density field plus this parameter FNL local times kind of quadratic Gaussian density field, Gaussian potential. In that case, we can compute that the Gaussian overdensity is getting enhanced by FNL times the Baryon potential. Now, which means that the matter density peaks in the cosmic field get enhanced. Now, we're not measuring the matter density field in our observations. As I was saying earlier, we're actually measuring the galaxies and hence the galaxy density field. And so we always have to relate them with the bias. And so what we can, in that case, kind of do is compute the matter part just with the Gaussian fluctuations and can essentially kind of absorb this effect in the bias, which then, if you kind of do this kind of with the kind of quadratic local non-Gaussianity, we find this characteristic 1/k scaling. And so this is then kind of what we see here in the galaxy power spectrum. What's kind of less known is, so this now, if you look at the archive and you see, as also in the last few days happened, papers in the context of large-scale structure, as well as we measure primordial non-Gaussianity, what they're always implying is local primordial non-Gaussianity. So this, the non-Gaussianity of this kind of squeeze type. However, in addition, there's of course, there's not only kind of predictions for this kind of squeeze type. In fact, the squeeze spectrum could actually be 0 from inflation, and other shapes are much more prevalent. And so these other shapes also produce a similar scale-dependent bias as I was just showing you from local. For instance, in a for the experts in the room, in a quasi-single field setup with an additional light scalar field, we can kind of relate the exponent of the scale-dependent bias, this kind of 1/k², to kind of these additional massive fields by kind of introducing this exponent delta that kind of then ranges from 0 to 3/2 or potentially kind of 2. And so what we get is for local, we have the scaling of 1/k². For equilateral, so if the non-Gaussian kind of triangle has kind of three kind of equally kind of sized sides, in the limit of kind of k to 0, it's scale invariant, but we have this additional factor of the transfer function in there. And so in general, we get kind of this kind of 1/k² minus delta scaling that we can look for in data. And so that's what and so in that case, what we have is we trade an enhancement on small scales. If we tune this factor of delta from 0 to 1 to 2, we trade an enhancement on the smallest, on the larger scales to an enhancement on the smaller scales. And so what we can do is we can look for it in data in kind of two different ways. One is we can either compute the correlation of kind of different types of non-Gaussianity, which is shown here. I'm going a bit fast given time. So if you're wondering about that, kind of ask me kind of after the talk. And what we can, given that the correlations of different kind of exponents is pretty large, we can actually just use measurements of essentially local and equilateral, and then kind of just extrapolate the measurement using that correlation that I just showed, getting these constraints from a kind of a Bos-Diotroff analysis. At the same time, we can, of course, also directly measure it by kind of varying kind of delta. And so that's what we did in addition. And we see that except for kind of around here, around kind of delta of 1.2, where the correlations are with 0 and 2 are small, we actually can do a pretty good job by just kind of do the easy analysis of kind of this point at 0 and 2. And so in the future, this kind of will kind of improve quite a bit with kind of Bos kind of being up here. And so especially because spherics will kind of go down to kind of FNL local on order 1. Now, these values here, of course, 10 to the 3, 10 to the 4 are very large. That's the reason for that is because we have huge degeneracies with kind of standard galaxy bias. And so adding in particular the bispectrum, which is on our list, will kind of bring this down quite a bit. And so with that, I want to conclude by saying that given kind of the theoretical insight over the last kind of 5-10 years that we gain in various observables, as well as the observational control that we have, especially on the power spectrum, we can now really do kind of even more and more analyses and tease more and more information out of our observations, as I was showing, for instance, on the free streaming nature of neutrinos or primordial non-Gaussianity, as well as all these kind of other things as well. And so with that, I thank you for your attention. And I'm happy to answer any questions now or for the rest of the day.
It's impressive to me that can you go back to the constraints slide? Yeah. That stage 5 spectroscopy mission or experiment is barely better than spherics, which seems.
Well, I mean, so spherics is.
Was tuned up for this.
That's I mean, like essentially like was built to go after FNL local. You know, so it really kind of wants to measure kind of a huge part of the sky, and kind of very kind of deep kind of redshift coverage. Yeah. And so the redshift coverage is essentially kind of similar between, I think, spec S5 and spherics. It's just that the number density for spec S5 is higher, and so. But so like especially where local lives, that's already in the shot noise is already kind of way below the signal, and so then we just get a bit of a boost by having a bit large kind of redshift coverage and a bit of a better anchor on smaller scales. And you see that in that limit, the difference is a bit that's a factor of 2. Yeah. Okay. It's a log plot here, so here's a factor of 2. Partly because a lot of that power is just kind of sucked up by degeneracies with galaxy bias, and so so I assume that the difference might become larger once we add the bispectrum and higher order spectra, for instance.
And then your super experiment, the purple line, what kind of thing would that be?
So that is we've just assumed we have a spectroscopic survey that's with a constant number density of redshift from 0 to 5, okay. With like 10 to the 9 objects. So essentially, in some sense, like a spectroscopic follow-up to LSST to even larger redshift or something like that. over the half the sky in that case.
What's the CMBS? You got a Planck bispectrum on there?
Yeah, the Planck bispectrum is here.
And then what's CMBS
and here.
Do you have any estimate for what CMBS4 is going to do?
I can look it up. And so we definitely have a plot, like a summary plot in the Snowmass inflation white paper. I think it's a factor of kind of a few better. So yeah, I mean, like the CMB will be kind of competitive with, especially for equilateral. That's still going to be the name of the game. There's some hope maybe with line intensity mapping to high redshifts that we can kind of get kind of. I mean, okay, we will be getting to. Especially, okay, if you use the bispectrum information, we will be able to get better than Planck. That's definitely the case. Beating the CMB will be more difficult in public, and getting to order 1 will be extremely, extremely hard. Go?
So how would a line intensity mapping experiment beat a perfect survey out to redshift 5? What information does it have?
So one, in principle, you can go to even higher redshifts. I mean, for example, Puma is targeting to go to like redshift, up to redshift 6 or something like that. Now, especially for these kind of very high redshifts in a spectroscopic survey, they of course like very kind of expensive in the sense that we need a very long exposures, and so the number densities will be kind of relatively modest. So actually, like the number densities of like this 10 to the 9 object survey is worse than kind of any of these. And so especially kind of when you talk about kind of equilateral, so if you want to kind of get the information from like the smaller scales, then at some point we have to contend with shot noise, and then can hope that with like line intensity mapping, we can access these modes at least kind of part of those modes.
Okay, so that purple line is shot noise limited.
Part of it, I have to look it up, but I think part of it might be.
Okay.
Or at least we get into the regime where it gets comparable. But I have to look it up. I'll get back to you.
What's happening at the turnover? What's happening?
This part here?
Yeah.
Yeah. I mean, so this is something so this paper is forthcoming, hopefully in like about a couple of weeks or so. And so there we actually have look quite in detail how the information moves from the smallest to the larger scales. And so the reason of this here essentially is related to degeneracies with galaxy bias parameters. So higher order galaxy bias parameters. Yeah. And so we actually see, I can show you a plot later, that if you kind of marginalize over more and more galaxy bias parameters, this turnover shifts to smaller and smaller scales. So if you don't marginalize over any, if you just look at FNL, fix all the bias parameters, essentially we have like a more or less straight line.
So, yeah, I know you don't work on observations, but I'm just wondering if you have thought about systematics affecting these things, given the recent results.
Yes. So I guess with the recent results, you refer to the DESI kind of photometric target sample analysis for local primordial non-Gaussianity. So yeah, okay. One is, so there's I guess when I'm talking to observers in particular, also we're part of that, they say, well, like photometric data is comes with additional challenges and whatever, and so they hope that with a spectroscopic sample, things will be kind of much better, much easier. But even with the photometric sample, essentially the main systematic are just the large angle effects. Given that like these scales here, or these modes, it's really kind of, you look over like half the sky, or like really kind of large angles. And so having that under observational control is hard, given that it's not like you look at these galaxies kind of one patch, but it's like very different days, and so like the seeing might be different and all these kind of things. And so like these large angle effect, that is something even in a spectroscopic sample where they really have to get under control. But for the magic sample, like in that paper, they do have a list of systematics that they looked at and that could potentially be a problem. I don't have them on top of my mind, but yeah, it's essentially for local, it's like these large scales, which in principle are kind of very kind of pristine, but usually kind of require different exposures, etc., and kind of very different parts of the sky. So there could be a lot of between us and it's like extinction and things like that.
There is a question on Zoom.
Okay. Oh, sure.
I don't know.
This is Brian Fields calling from the dark sector. So thanks for your beautiful talk. So I was just wondering about I love how you separate out the effect of the phase shift. That's really interesting. When you do that with the large scale structure, you showed us that when you added the CMB, you get you just passed by it. Yeah, you get a tighter measurement, but the ineffective is pushed out, to sort of unphysical or much larger than the standard model. So, is there a simple way to see what happened? I understand that that's just preliminary, but is there a simple way to see what happened? Like what?
Yeah. So essentially, we see that the mean value of alpha between just like the BO measurement and the CMB value is somewhat different. And given that we have this large degeneracy line, that then we kind of just push kind of higher in this higher corner. I mean, we knew going in that this was very much a possibility, that we either kind of sketching low or sketching high or something like that. But yeah, I think one shouldn't kind of read too much into that.
Sure,
it's very much a first analysis, showing what in principle is possible, and then I think with DESI it will all be kind of much more interesting than with BOSS.
Yeah, that's cool. That's really exciting. Thanks.
Sure.